Welcome to a lesson with Dr. Powell. Let's take a look at how we can represent maps or functions between Z modules that are free. In particular, how we can represent a map that comes from a free Z module. What is a free Z module? A free Z module is a structure, it's a set that has an action by Z on it. So here, let's come up with an example. Suppose we take like Z3, which we'll think of it as Z cross Z cross Z, meaning tuples of elements in Z, such as 1, 3, and 0, say. Okay, so this is an element of Z cubed. Now it has a nice outside multiplication by Z that gives a module structure. It's scalar type multiplication. We can say something like 5 times 1, 3, 0, and we get 5, 15, 0. It just multiplies in component wise. So that's what this is a Z module. Now I claim that it's a free Z module. What makes it free? So what makes this Z module free is that whenever I have a map that preserves module structure coming from it, so a map or a function, say, that comes from this that preserves the addition structure here, as well as the outside multiplication structure, such that if I have something like f of k times something, it's going to end up, the k can travel outside. That's what it means to preserve the structure of the outside multiplication or the scalar multiplication. Also, it preserves addition. So anytime I have this happening for a function coming from Z3, then I can represent this function in a very nice way. This function, if this is free, depends completely on where just a few of the elements in here come from. Namely, I say that Z is free, or Z3 is free on what we're going to call a basis, or a set of 3 things even. This is a basis of 3 things, namely 1, 0, 0, which I'll call E1, E2, 0, 1, 0, E3 we'll call 0, 0, 1. So we're going to take these guys right here, and this function that comes from Z3 can be completely defined and determined on where it sends each one of these basis elements. So a Z module is free if just knowing the images of these guys for sure can tell me the images of everything else. Of course, a different module would have a different basis, but it's going to be free with respect to whatever basis I pick in that sense. So let's see how that might go. All right. So let's see here. If we take, if we suppose that f1, 0, 0, or f of e1, say, maybe we'll just write f of e1 for short. And we need to have a codomain of where it's going to land. Let's suppose we make it another module, a Z module, that has a basis in the same way. Now, we're not showing necessarily that it is free. But we'll assume or take for granted right now at the moment that it's free, that it has that property, that no matter where these are sent, that's going to uniquely define what this function is going to do. Now let's suppose that the codomain is Z2, so ordered pairs in the integers. So the image here could be anything like, let's suppose it's something like 1, 2, f of E2, let's suppose that's something like 3, 5, and suppose that f of E3 is equal to 0, 1. Okay, I'm going to put all of this data into what I'll call a matrix as follows. So the image of E1, I'm going to put it right here as a column, kind of in the first position, denoting E1. Second image, E2, I'll write as a column 3, 5. The third one, I'll write as a column 0, 1. So this matrix encodes the information of where each one of the standard basis elements, these are the standard basis elements, where they are sent. Okay, is that really going to help us know where to send anything in Z3? Well, let's just try it out and see, actually. It's pretty clear. If a function preserves module structure, then for sure it's going to be able to preserve, we're going to know where to send anything. And we'll see exactly why. Okay, here we go. So let's suppose that we have f of 2, 5, 6. Where is this going to go? Well, let's look at 2, 5, 6. We know that 2, 5, 6 can be written as 2 times E1 plus 5 times E2 plus 6 times E3. Try it out and see. 2 times this plus 5 times this plus 6 times this should come up with that. Well, that's it. Since we can represent this uniquely in terms of the basis, we're set to go. Because if we're preserving the structure of addition and outside multiplication, notice that when we take an image of this, we're simply going to get 2 f of E1 plus 5 f of E2 plus 6 f of E3, because f splits across the multiplication as well as the addition here, sending the multiplication to the outside of it even, and then the addition is being sent to the outside as well, to the into the image. So operations in the domain are transferred nicely to operations in the codomain. That's what it means for the operations to be preserved or transferred by the function. So just based off the assumption that the operations are transferred, we know that the image of this is precisely this. How do we figure out what this is? All we need to know is what these images are. F of E1, F of E2, and F of E3. That's all we need to know. So, well, this matrix right here encodes the information where each basis element is sent to. Okay, how can we use that? Well, let's think for a minute how this would work. If we want to plug in 2, 5, 6 into this function f, notationally we can write that as a column 2, 5, 6. So then this expression, this matrix with a dot and this column is the same thing as writing down f 2, 5, 6. You might call this matrix multiplication, but really you can think of it as composition, or putting one thing into another. You're putting 2, 5, 6 into a function, and this is a function. Every matrix is kind of like a function, or if you will, the output of some function, or maybe just a statement or something to plug into something else. So this multiplication symbol means nothing other than plug this into this function. But understanding what this function means tells you exactly how to plug this in and tells you exactly what to get out. Let's see how. Okay, so let's take a look at this, maybe right over here, and see what this is going to be. Okay, so, well, notice to find this image, all we have to do is take 2f of v1 plus 5f of v2 plus 6f of v3. What's f of v1? It's what's in the first column right here. Remember that it lives in Z2, the codomain. That's the image, and we take 2 times it, and we add 5 times this column, f of v2. So 5 times that column, 3, 5, plus 6 times the next column, 0, 1. And we simply just compute this, and that's it. That's all it is. So we can go across the top if we want. 2 times 1 plus 5 times 3 plus 6 times 0, which is simply 17. On the bottom, 2 times 2 plus 5 times 5 plus 6 times 1. So 25 and 4 is 29, plus 6 is 35. So we end up getting this as the image of 256. So 256 is sent to this via the function f, which goes from this free module over to this one. Notice that anytime we have a tuple of integer numbers like this, that lives in, or a module that represents tuples of integers like this and this, these are actually free Z modules themselves, and maps between them can always be represented by matrices. If you've ever done matrix multiplication, this is the same thing. You can check. What we did is we did 1 times 2 plus 3 times 5 plus 0 times 6 to get the 17. And notice that's what we did across right here. But thinking about it in terms of just taking multiples of columns and adding them together is very instructive and provides some good intuition. Thanks for watching.